Hello, my name is Aaron Mazzeo, and we are going to go through the code for Lab 2, Modeling a Bouncing Ball. This work, of course, builds on that of Jon Singer, Rahman, Pejman, and others, and it's my pleasure to get to present it to you. So we're going to have a ball which starts 100 meters above the surface of the Earth, or a flat wall. We're going to initialize the variables. We're going to have an initial horizontal velocity of 50 meters per second. We're going to run our simulation for 30 seconds, plotting the data 4 times per second. And we will have gravity and a drag function eventually influence the travel of the ball, or the motion of the ball. And then near the end, we will be able to apply periodic boundary conditions. Let's go ahead and get started. We will go to MATLAB and open up a new editor file. And the only other file that we should have in our directory is this gravity function, which we defined previously. You might find it useful to do some copy and pasting from the code from the first lab, but for now we're just going to have the gravity function and an empty open script. As we generally begin, we'll put CLC, clear all, close all in here, and then we'll use initial variables, M1 for the mass of the ball. It's a pretty big ball. We're going to say that this is having a mass of 100 kilograms. The Earth, of course, has a much larger mass, and nearly 6 times 10 to the 24th kilograms. Okay. Then we're going to specify an initial location along with an initial velocity for the ball. And when I do this, I like to set it up. You could do just R, but I'm going to do R not, so that I know that this is the initial location, even when if I have to do loops or other things in the future, when it comes back to the beginning of the loop, it's where I'm starting. When I mean loops, I mean, let's say you're doing loops over DTs or time steps or other things. You want to make sure that you start with the same location every time. We can figure out the distance of the initial location from the center of the Earth, and that's what this is. This command is doing. We use this command a lot in the first lab. Okay. Okay, that's in meters, of course. We have its initial velocity, and we said for that it was going to be 50 meters per second in the x direction. So we'll go back over here and say V naught is going to be 50, 0, 0. And this is going to be initial velocity. Capitalize, not capitalize, fine, not capitalize. Okay, and then we're going to have that speed associated with the initial velocity. So this is a scalar quantity. Okay, and then we can decide on what we want to keep track of as we iterate in time. So maybe we want to keep track of the x's, the x positions. So x And initially, the first thing in the container, I do like to load the container up with the initial parameters, with especially with a one indexed matrix system that we're using here with MATLAB. And should be good like this. I guess I could put a square bracket around here, but or here, but that's not really necessary. I could probably just leave that as 0. So either way, I guess why not, just so we know that they are containers. Okay. And let's see, there's a highlighting here happening, so I'm not quite sure. I just want to, normally I don't run the code this early in that thing, but that's, let's just see it running. And we'll call this bouncing ball. And we'll call this V1. There's going to be a couple of things that we end up doing, but we'll do bouncing ball. Okay, it seems to be working okay, from what I can tell. The warning is, not sure. I don't know. That's okay though. Line 2. All right, well, let's not get distracted. Keep going. So the DT time step we're going to set at 0.01, so 100th of a second. And we're running for 30 seconds. That's 30 seconds, yep. Okay, and then the number of iterations or steps in time we're going to take will be that total time divided by the time step. And we can do a floor on that to make sure that we get a natural number that we can run in our in our for loop. And we're going to be sampling 4 times per second. And this could be, of course, an issue if you are going to try to record data or have a time step that is larger than this kind of sampling or recording of data. Okay. We'll say that k equals 1 for the index of our saving. Of data. And now we'll also put a figure up for us to see to present data. And this figure is going to be one that shows the x and the y position of the ball. And so for that, we'll do an x label. And we'll do a y label. And this is going to be the z. So nothing's happening in the y direction for this problem. Okay. And then we'll go about thinking about our wall for a little while. Okay, so how, great, because we've got this simulation where it's got to bounce off something. Right, it's a bouncing ball. And it's going to be bouncing off of a flat wall, essentially on the surface of the Earth. How do you define a wall? Well, our wall is going to be a plane in this case, and for that, whoops, sorry, keep going. Okay, we can use a location and a normal vector. So we have an RW, we'll call it, and we have a vector normal to that wall. So for this, we'll say hard wall boundary condition, and we are going to say that its location with respect to Cartesian coordinate system, which we're using, is going to be on the surface of Earth. So you recall that we are starting the ball 100 meters above the surface of the Earth. Okay, and so this is the radius of the Earth, and so the wall is just going to be on the surface of the Earth. So it's essentially what we had R naught here with this z minus this 100 just puts us right back with the radius of the Earth. So this is going to be the location of the wall or ground. And then we have an opportunity to also think a little bit about the slope of the ground. And we'll say this is going to be done in degrees. Okay, so right now for this lab we're going to say, okay, the ball is going to be on a horizontal, bouncing off a horizontal wall. Okay, and the normal vector, right? We said, where is it? Here, right? This normal vector coming out of the wall is going to allow us to define it, and of course that's dependent on the angle. So here you can do the sine d, which means if I were putting this in degrees, and I need to do appropriate sine function or sine of that theta, and that's in degrees, I can just do sine d instead of multiplying the input by pi over 180 to get us in radians. So it's a kind of a nice feature that MATLAB has for us. I'm sure many people, including myself, have made mistakes in the conversion between radians and degrees. Okay, so now we've got our wall. Now, what we'll do here is begin to say what R, big R, okay, so that R vector, and the speed R, and the velocity vector, and the, wait, did I say speed already? I meant, so this is the altitude, this is the R vector for the actual position in space, this is the velocity vector, and then this is going to be the initial speed. Okay, and you know, it's like, it may look repetitive, right? But if you were to put a loop, say right here where you're going through the different time steps, right? Now you can ensure that you're starting off with the same conditions, initial conditions every time. We're going to create something called a bounce counter, all right? And so this is not, it has not hit the wall, so it hasn't bounced yet. So we're going to say that okay, that's that. And then we're now ready to simulate the loop, okay, with the behavior that's happening. Okay, so for that, we do a for, and we're going to go from the 1 to the number of iterations that we have. That was right here, so Imax. And now we can implement Verlet, and we're going to use the Verlet Spring 24 that we used last time. So the first thing we do in this description of Verlet is to calculate the half velocity. In order to calculate half velocity, we are going to need to calculate the acceleration. And so for that, we're going to use the gravity function. And this will calculate the magnitude of the gravity, and then this will become a unit vector. So we still have a force, which is going to be a vector. We can figure out what the acceleration is as a vector. So we take that force and we divide by m1, because that's the ball that we're interested in. And then we calculate out the half velocity with that acceleration, and we can update the position. So do we make it look nicer? I don't know. It's not necessary. I guess I kind of sounds like playing a video game or something, having to enter all those spaces. So we have the position now updated, and we can figure out, or we can update our distance from the center of the Earth as well. So distance from center of Earth, right? Or that's a radial distance, however you want to look at that, or it's altitude. Okay, like that. Okay. And we know where we are in space, I guess, or I guess 100 meters is still in atmosphere, but you get the idea. You know where we are relative to the center of the Earth. But where are we relative to the wall? Okay, and so as we described, because that's important, right? We want to know if we're hitting the wall or if we've gone past the wall. We talked a lot about this in our session together, right? So how do we know if we've crossed the wall? Well, we need to figure out a distance that we are from the wall, okay? So if this is RP, right, and this is the location of the wall, right, we can figure out a distance vector, okay, which we defined as RP minus RW, okay, and that's the distance from whatever coordinate, right? So however, you could define the wall to have this this distance, okay, to here, for example, right? But this is what we said is our coordinate for the wall, right? There could be multiple coordinates with this NW, but here we go. So dW is going to be RP minus RW, okay? So that allows us to figure out, okay, where we are relative to. So RP is, right, the vector describing the position of the ball, and we said RP, but in this case in our code we're just using R. So it's R minus location of the wall. And this is going to be a distance to the wall coordinate, you could call it. All right. Now, the next thing we asked ourselves was, how did we figure out whether or not we had crossed the wall? If we are above the wall, we just let gravity and later drag do their thing essentially on the wall, or not on the wall, on the ball. But if we have gotten into a situation where we've crossed the barrier of the wall, then we need to update and we need to be able to change the effect that we have on the ball. Okay, so to do that, we're going to check if we've crossed the boundary of the wall. Okay, like this. And so this happens, this crossing would happen if the dot product of this distance vector and the normal vector from the wall is less than or equal to 0. We discussed this last time. So we haven't crossed if it's greater, and will it work? And it does cross if it's less than. Okay, so the ball is going along. It's now crossed, or we're checking to see if it's crossed. And if it's crossed, then what do? Well, we need to update the velocity and we need to update the position. So for that, we discussed how we could update the velocity. Okay, so you have a new normal velocity, okay, coming out of the wall, right? And we have a parallel velocity, okay? And so the equations that we wrote for this are as we see here. Okay, so this is v2n, right? So this is going to be the new normal velocity, right? This was the velocity that I had before it hit the wall. And then we have a v2 parallel. This is the velocity parallel. Okay, so this is normal velocity, parallel velocity. And then let's go back to here. So we have a Vn, which is going to be the normal velocity. We dot the velocity with okay. So where was that? That's so we're dotting the velocity with the normal vector, and then this normal velocity, right, is in the same direction as the normal vector, and this is a unit vector, so we don't have to divide by its magnitude. We just know it's a unit vector, so this will tell us v2n. The projection, right, into this normal vector, that's, you know, of this, so this projected into this, right, is going to tell us, hey, it's going back. You see, this is going this direction, this is going that direction, that's going to be a negative sign, and the amount that's projected, that's essentially, right, its vertical component, its normal component to the wall. Okay, so we got that. And then the parallel component can be given as follows, and that comes from looking at what we have here. Okay, so this vector plus this vector gives us this vector. Okay, and this is a lossless, or it's an elastic collision. It's lossless. So the magnitude of velocity coming in to this wall is going to be the same as the magnitude coming out. So we have Vp equals V minus Vn, and the new velocity can be thought of as Vp minus Vn. So this is the new velocity, which keeps the same parallel component. While flipping the normal one. Okay. So we've updated velocity. We need to update position. How do we update position? Well, we can go back, and that I'm not going to go through all this right now to save us some time. Okay, but that's a multi-step process. Okay, and we were actually kind of already said how the code should be implemented. Okay, but we're going to be looking at an Rn, an Rp, okay, and then R, the new R, so RP2. Whoops, whoops. Oh, okay, RP2. Okay, so let's go back here. Okay, so now we've got to update position, and we have a RN, and that is going to be dotted of the distance vector with the normal vector of the wall times the normal vector of the wall to make it a vector, and then we figure out what RP is. That's going to be, and that's not the RP that we of the particle or the ball. That's parallel. Okay, so I guess I should have been careful here. This is VP. This is VP. This is parallel. I use parallel in the slides, so it's not exactly. Okay. Maybe if I were better, I would have the variables be exactly the same, and the slides and the code. Okay, but that is how we figure out what the wall has done to the ball. Okay, so now we threw that right in the middle of Verlet. So this is just half velocity, right? And we've updated the distance. We need to do the second half of the Verlet integration. And so we're going to do second half integration, and now we're going to figure out what our speed is, because we just updated it, right, here. And we're going to, although we at least we believe the speed should be the same, okay, if the hard wall is, if it's conserved. So, this may not, the speed that we had coming in, all right, might be okay, but we actually are just using the v. We haven't really even calculated one in this iterative loop, right? We have one here, okay, but so now's a good time to calculate it, okay? So this is the speed, and we're going to use the force. We do have a new position, right? So that's definitely something we want to input into the gravity function to figure out what the acceleration is. And of course, small time steps, small changes, but we have to keep accumulating them. And now we can update another half velocity like that. Okay. It's so funny. I'm just like, hey, any questions? Of course, I can't. Maybe there are questions, but this is not an in-person experience. Ask the TA who is with you right now. Okay. So now we're going to do some recording. All right. We're gonna do some plotting at different fourths of a second, I think we said. Yes, we're going to do 4 different, I record is fourth of a second. So this is, and we do it with a modulo at 0. So this is going to ensure printing on the fourths of a second. Okay. All right, so this is working out okay. Here's our plotting. And we're just going to do plotting of the x and the z component. We're doing a draw now. And then we'll increment our saving data. keep track of our x. Now, whoops. Notice that we incremented this, right? Because so like if we were in the first time step, right? xs of 1 was just r 1, r of 1, right? We look back at this. Okay, see, you remember that? R naught of 1, right? So R1, sorry, R naught of 1. See, I can't even keep track of everything. So this would be like if you're in a second, you know, or if you've gone a fourth of a second, now we've got the second member of our x's vector, and we're going to put in the x coordinate that we've calculated. And for z, we're not saving, nothing's happening in y, so we're not saving those. And let's see, we have an altitude that we're saving. For distance from the center of Earth. Okay, and we have, yeah, so this, speed, that's kind of nice to save. You know, we're saving these things, but I'm not saying we're necessarily going to use them in this example, but nonetheless, it's nice to have this outlined. And okay. Okay. All right, so then now what's also kind of fun is that we can, in our plot, we can have it tell us in the title, that's a good place to put these things, what time step it might be. Okay, so this will tell us, right, what we expect is it to tell us in fourths of a second where we are. Okay. And that one, I think that's it. Okay. So note, there's no drag, all right? So there are things that we have done and things that we have not done. One thing we have not done, okay, if we can go down, we have not implemented a periodic boundary condition yet, and we have not implemented drag, okay? But we have used gravity. So let's see what the ball, let's see if this works, okay? Let's see, so we're gonna do a Control Enter, and it says it's busy. Oh, okay, what did I do? Oh, so it's not happy about that. I did something wrong there. Oh, that's what I did. I forgot a bracket. Okay, so let's try that. Okay, so now what else did I do? So now because that's unbalanced right there. Okay. This is embarrassing. Line 85, column. Okay, what is going on here? So num to string, this is finishing this. Ah, that's why. Okay, you gotta keep your bracket straight. Okay, so now here it goes. And remember, we're supposed to go for 30 seconds. And we're seeing the X and the Y position. Or sorry, X and Z position. Okay, as it moves along. And it stopped. All right, so that's 30 seconds. And it came back to its original height. Okay, now that is, well, even if there were drag, this wouldn't be completely realistic. Completely realistic because the ball is conserving its momentum on the hard wall boundary. But we're using a hard wall boundary. We'll try to make it a little more realistic, and we'll add drag. So what we're going to do is create a drag function that allows us to essentially have the ball experience some drag as it's going on its jolly way. Okay, and where's that drag going to be influencing things? It's going to be influencing things right here where we have gravity acting on the ball during our Verlet integration. Okay, so we're going to create a new function called drag. And we can define this function f drag as operating on a coefficient of drag, a density of the medium, or well, we don't have media, I guess, so the medium surrounding the ball, the radius of the ball, and the speed of the ball. Okay, and then this is going to be returns the drag, force, and air. So we're going to be using air, and for that we can define a drag well, you could say, yeah, we're going to be, we have a CD, so we have a coefficient of drag, and then we have a drag times, or a D, we'll say, times the velocity squared. All right. Actually, I don't know if I like it this way. I think I'm just going to do it this way. I'm going to say force, drag force is equal to 1/2 times rho, the density of the air, times the coefficient of drag, times pi, times the radius squared. Okay, so this is, what is this? Remember, it's CDA, so it's 1/2 rho CDA, so that's going to, the frontal cross-sectional area, so pi radius squared, times the velocity squared. Okay, and this will give us drag, like that. Okay, I think I did that right. Yep. Okay, so we'll save it, and MATLAB's pretty smart. It knows that I want this drag function to be called f drag right here. Okay, I think that's good. CD, rho, yeah, just like that. So now we go back to our bouncing ball, and in this case I'm going to, I kind of like having this lossless, well, drag-free one, and I'm going to just copy, and I'm going to Control C, I'm going to paste, I'm going to go ahead and make another script. Okay. Whoops, I didn't want to open it yet, I wanted to rename it. So we're going to call this bouncing ball, and yeah, it's really small over there, right? So bouncing ball, and we're going to call it with drag. Okay, so I guess maybe you can't see that because it's really small, but anyway, that's what it's called. And then I'm going to go back because I think the editor real estate is probably more important. So now I'm going to open this one up. And I make mistakes, but in terms of, okay, I accidentally changed the script, and it makes me sad when I, lose or change something that I didn't want to lose. Okay, so for this, remember the drag, the drag function, it needs some parameters, so we should probably give it a CD and a rho and a radius, okay, and which are constants, right? Those aren't going to be changing, but the velocity, of course, will be changing. So I don't know, we can probably do this kind of up near the top. Let's see where I did it. Yeah, we'll do it even before, right above here. Okay, so right after the hard wall. So we're going to define constants associated with drag. Okay, and so we have a CD like that, which will be our coefficient of drag and air. Wow, cannot our density of the air. Okay. At least at close to sea level and standard temperature. And we'll say the radius. And that's going to be in meters. Yeah, so that's, you know, that's kind of like a satellite, I guess, right? Or I don't know. Yeah, it's bigger than a 10 by 10 by 10 centimeter CubeSat. That's for sure, right? So okay, so now we've got our CD, our rho, and our radius. Where do we implement this drag? Well, we're going to implement it where we are also adding gravity. Okay, so in this case, okay, we have a gravity. Now we're going to say that there's going to be drag, okay, like this. Okay. Okay, so this is going to be gravity, okay, and we're going to be having drag acting on it, okay, and notice something here that's kind of cool, that the velocity, so I'm like, oh, you know, is the drag being implemented in the same direction as gravity all the time? That would be kind of interesting, wouldn't it? That also kind of be a problem, right? Because you know, if the ball is traveling downward, right, gravity is pulling it down, but the drag is actually going upward. But that's taken care of by having the velocity vector here. Okay, and this is a unit vector because we divide by the speed. Okay, so that's one location. I think I'm missing a parameter. I think I need the radius, right? Yes. So radius as well. Okay, like that. Yep. Okay, and then we come down here, and we're going to do the same thing. Racus. Okay, just like that. So this is, maybe I'll put a comment that this is gravity, because it's weird because it's minus minus, but that's fine. You get the idea. Okay, so now what we should see, if we did this correctly, is one, it should run, and we should see that the ball doesn't come up to the same height every time. Okay. And what do we see? Ah, look, see, it started up higher, right, and then it bounced, and then it came up to this, okay, and then bounced again, and it doesn't come back all the way to the height from the last bounce, right, because we have drag acting on it. And we're getting close to our 30 seconds here, just like this. Hooray. Okay, well, I don't know if it's hooray, but it looks like it's supposed to look. That's why it's hooray for me, right? Okay, so this is nicely implemented for us. Now, let's see what's remaining. I think the last thing that's remaining is just a periodic boundary condition, right? So how do we think about a periodic boundary condition? We think about it in terms of, well, I guess you could think of it different ways, but in our case, what we're going to think about is a pair of vertical, okay, boundaries, and as the ball travels along, and you saw that it was going to the right. So as it goes to the right, this is my right. Maybe this is your right, but anyway, as it goes to the right, if it crosses that boundary on the right, then we want to send it to the left. Okay, and so how do we do that? We can do that using modulo. Okay, and we talked a little bit about that, right? The Spider-Man thing, right? And you know, this kind of maybe a PowerPoint animation, but now we're going to do it MATLAB um, calculation. All right, so for that, we go back here, and for this, essentially, um, all we do is change it. So if it's a vertical wall, we had to just change the X location. So for that, we can do it, yeah, we can do it above the, well, we got to do it in the simulation loop, but we can do it maybe here before we check to see if we have interactions with the wall. We can say this is going to be affecting the X position, and we're just going to do a mod, okay, of, oops, okay, let's see, mod of the current position with some type of periodic limit, okay, which we have to define. So, you know, if it gets to 100 meters, right, then it puts it back at 0, okay? If it gets to 150 meters, right, we could say it goes back to 0. So we're gonna just say that this is adjusting only the X position. So for that, where should we put it? I don't know. The periodic limit is what I'm thinking. We got to put the periodic limit here. Let's maybe after we define this hard wall boundary condition. So we'll say periodic limit for, or maybe it should be limit for periodic. And this is a vertical. Okay, so periodic limit, we'll just say is 100 right now, and we'll say that's in units of meters. Okay, like that. Okay, let's see what happens when we run it now. Ooh, see, this is what happens. I made these changes, right? And I didn't create a new file. So I can save it now. I'll go ahead and do a save as, but I will have to go back and edit out my previous file because I think MATLAB probably already messed with this previous one. We can check. See this bouncing ball with drag. Okay, it probably already has, because MATLAB is doing some auto saving. Oh no, okay, it didn't add it there. Okay. Oh, I guess it's safe. It didn't do it. All right, great, because I didn't run it. All right. Oh, good. I sometimes, or I run it, and that's when I save it by accident, I guess. So let's see what happens here. Look at that. So it got to 100, and you see the time step, right? Maybe a smaller time step because like it's over here. It's kind of a significant amount, but then it came back over here to 0, right? But that's the thing when the you know, depending on the size of your time step, right? Well, actually, remember we're only recording 1/4. We're recording every quarter of a second, but we're running at 100 times per second. So it's actually not the time step's fault, it's the recording frequency's fault, okay? Or the sampling at which we're recording. So, you know, we go from there to here, and then it comes all the way, and it bounces, boom, right? And then it comes up over here, and then enters back over here, okay, bounces. Now I'm losing track of things. Yeah, it comes over here, and then it comes in like here, and then it bounces pretty close to that same location it just was at. Okay, and then it goes down to this location, which comes over to here, and then bounces over here, and then it bounces in, whoop, I think that's where it dies. Okay, so we've now accomplished what we've set out to do according to the lab statement, which was to to simulate the behavior of a ball 100 meters above the surface of the Earth or a flat wall. Initialize variables, run simulation for 30 seconds, plot data 4 times per second, and then implement gravity and drag force functions. And we were able to observe the behavior, and we applied periodic boundary conditions. Thank you very much, and I hope that this lab went smoothly for you. Have a good one.